Today's lecture is going to be learning some of the basic derivative shortcut rules. I told you that we would be learning these soon, so I'm going to go ahead and teach you a few of these to start off with, and then we can start using them. Now, of course, this isn't going to excuse us from knowing how to do the limit definition, but we are still going to need to know how to do that. But eventually we're going to just move on to just using all these shortcuts. So let's jump in here. So the first thing, there are four rules that I'm gonna teach you today. I'll just kind of jot them down over here. The derivative of a constant, the power rule, sum difference, and a constant multiple rule. So basically, let's just jump in. So the derivative of a constant. So I'm going to use this notation, d over dx, of c. Now when I see this notation right here, d over dx, this is, you got to think of this like a command. Thou shalt take the derivative of, and then whatever is here. And you're going to take the derivative with respect to x. Now in this class, we're pretty much going to stay with taking the derivative with respect to a single variable, so we won't have to get too crazy with that. But the derivative of a constant. So if you think about the graph of a constant function, how is that constant, or how is that function changing as you change x? Well, it's not. It's constant. So the derivative of a constant is 0. Okay? So that's the constant rule. The next one, the derivative with respect to x of x to the n. So this is how you take the derivative of x to a power. Like x squared, x cubed, x to the fourth, x to the negative 3, whatever. The derivative of x to a power is going to be n times x to the n minus 1. Okay? N times x to the n minus 1. So basically what happens when you take the derivative of, say, something like x squared, the derivative of x squared is just 2x to the first. Now, of course, no human being is going to write 2x to the first. They're just going to write 2x. All right? But again, take the derivative of x squared. Take the derivative of x squared. What does that equal? 2x. Okay? That's the power rule. So there's one. There's dos. Number tres. The sum difference rule. Okay? Basically, it just says this, that the derivative of a sum of two functions, okay, is equal to the sum of the derivatives. Basically, it just says, the sum difference rule says, if you're adding two functions together and you want to take the derivative of that sum, just take the derivative of each term individually and you'll be fine. So a quick little example of that would be, what's the derivative of, let's say, x cubed plus the square root of x? Okay? So I'm going to put this in parentheses. So what's the derivative of x cubed plus the square root of x? So we're finding the derivative function here. It's just going to be the derivative of each one of these term by term. Now, it's going to help us if we think of radicals as fractional exponents. So right away, anytime you see a radical, if you're going to execute one of the derivative rules, you probably want to jump on this fractional exponent thing because it's easier to use the power rule. So the derivative of x cubed is 3x squared plus the derivative of x to the 1/2 is 1/2 x. And then you're going to get really good at subtracting 1 and adding 1 from fractions. 1/2 minus 1 is negative 1/2. And of course, you could write 1/2 x to the negative 1/2, and I think you should be able to, and recognize that this is equivalent. Let me just write it up here. 3x squared plus 1/2 x to the negative 1/2 would be this, 1/2 radical x. Now, I'm not saying you have to write this like that, but you better be able to do that because you're going to see it both ways. So you need to be fluid to go back and forth between those. If you're just doing your homework and you get this as an answer, ain't no thing. Leave it like that. Or if you're on a test, you get that as an answer, leave it like that. Unless I tell you to put it in radical form, you can leave it like that. But you've got to recognize that sometimes that radical form is more beneficial. And I guess I got to erase the board here. So I'll pause the video so you don't have to watch me erase. Okay. So the last one, the last little derivative rule that we're going to learn in this video today is how do you take the derivative of a constant times a function. Okay? How do you take the derivative of a constant times a function? It's very simple. It's equal to the constant times the derivative of that function. So basically you can just pull constants out and then multiply by the derivative. What do I mean by that? A quick little example. Let's say if I have the function f of x equals, let's do a simple one. Well, let's do one that's a little bit more challenging. How about 7? Is that a 7? How about 7 over x squared? Okay? 7 over x squared. That's an embarrassing looking 7, but it's a 7. So the first thing I'm going to do when I go to do this is I'm going to think of this, I'm going to rewrite the function as 7x to the negative 2. Okay? Now why would I use 7x to the negative 2? Because it's easier to do the power rule. You know, I can subtract 1 much easier when it's like that. All right? And so now, if I'm going to use this constant rule, this is, if you want to think of it, this is really like 7 times x to the negative 2. So it's a constant times a function. And the rule is, it's the constant times the derivative. So the 7 is just going to hang there, and then I'm going to take the derivative of x to the negative 2, which is negative 2, x to the negative 2 minus 1, negative 3. And then I can clean that a little bit. Negative 14, x to the negative 3. And is that answer acceptable? Can I leave my answer like that? Yes. But you also should know, friends, that that's equal to 14 over x cubed. And you shouldn't freak out if you go, if you see this, you need to be able to go fluidly between those two. It doesn't matter how you leave your answer. It's more important that you understand that they're equivalent. Okay? So what I think I'll do right now is I'll erase the board, and we'll just do a few examples of these all mixed together, and then I'll give you some to practice on your own. Okay, here we go. Examples. All right. So we're going to do some examples now. So I'm just going to make up some functions off the top of my head, and we're going to take the derivative of them. By the way, sometimes when we say take the derivative of, that's the same thing as saying differentiate. We're going to differentiate these functions. Means take the derivative of. So first example, we'll just say, how about f of x is equal to, how about 3 over x to the 4th plus 7x squared. Okay, two functions added together. So we're going to just take the derivative. But before we do that, sometimes before you take the derivative, it helps to rewrite the function. So there seems to be an obvious thing that I would want to rewrite this so I can execute one of those rules. How about I write that as 3x to the negative 4th? There we go. Beautiful. All right. So now we're going to take the derivative. Here we go. Now you can start doing these in your head, man. Like, you don't have to break these rules down every single time. So the 3 is going to hang, or you can just do this in your head to bring down the negative 4. Negative 4 times 3, negative 12, x, negative 4 minus 1, negative 5. Boom, that one's done. Next term, 2 times 7, 14, 2 minus 1, x to the first. Boom, that one's done. Okay? So the derivative of this function right here is equal to this. This is the answer that we would get if we did that limit of f of x plus h minus f of x over h as h goes to 0. This is the answer we would get. But we don't want to do all that algebra. We don't want to do all that limiting stuff. I mean, that's terrible. It's what you do to torture people with. So here we go. We got this rule, and it's great. Let's do another one. How about, let's use a different name for a function. F gets all the love. How about g of x is equal to, how about this? Ready? How about 3x cubed plus 2x minus 1 over the square root of x. Okay? Now you might be first looking at that saying, oh my gosh, Mr. Mitter, you didn't teach us how to take the derivative of the divided by two things when you're dividing two things. We had a power, and we had a sum and a difference. Well, we didn't have anything with dividing, and you're right, I didn't. And don't be tempted to think that I can just take the derivative of the top and the bottom, because it doesn't work that way. There's a quotient rule that we'll learn next time. So in order to take the derivative of this guy, we're going to have to rewrite this function. Don't hesitate to rewrite things. And this is almost a rule of thumb, guys. Anytime you're dealing with a function that just has a single term in the denominator, like a monomial in the denominator, it's almost 9 times out of 10, it's easier if you bust that thing up into separate fractions. Okay? So I've broken that into 3 separate fractions. And now we got an algebra problem. We got to deal with this, okay? So we got to think about what these things are as exponents. So 3x cubed divided by square root of x, which is the same thing as x to the 1/2. So what is this first term? How is that going to simplify if I put it with a fractional exponent? Well, we would say x to the 1/2, and that's 3. So 3 minus 1/2 is 2.5. So this will be 3x to the 2.5. Yes, that's the same thing as 5/2. We can write it like that later. Plus 2x and radical x, that's going to be 2x to the 1/2 minus 1x to the negative 1/2. Okay? Still have not taken any derivative, have not done any calculus yet. This has all just been algebra fun. Now we can take a derivative. We can use a rule. So here we go. We're going to take 3 times 2.5. So what's 3 times 2.5? So that's 2.5 plus 2.5 plus 2.5. That's 7.5. X to the, what's 2.5 minus 1? It's 1.5. And then plus 2 times 1/2. Bring that exponent down. 2 times 1/2, 1. X to the 1/2 minus 1. Negative 1/2. Minus negative 1/2 times 1. I'm sorry, negative 1. Negative 1/2 times negative 1. Positive 1. X to the negative 1/2 minus 1. Negative 3/2. Okay? Guys, that's an answer. That's a correct answer. It looks kind of not traditional. People might say, oh, that's not in radical form, but it is correct. If we want to put it in radical form, and again, we don't necessarily have to, but we've got to be comfortable with it. X to the 1/2 is the same as x radical x, plus x to the negative 1/2 is 1 over radical x, and then x to the negative 3/2, that's also the same thing as negative 3/2 is the same as negative 1 in 1/2, 1.5. That's plus 1 over x radical x. Okay? Both of these answers are correct. They're both the same level of correctness. You need to be comfortable with this, but I'm not going to always make you do this. I mean, there's going to be times where it's just not necessary. But there may be a time where you need to recognize x radical x is x to the 1.5 so that you can do some other calculus, and that makes the other calculus easier. So it's not like I don't want you to ever simplify anything. I want you to be comfortable with simplifying things. Okay? Both of these are correct. Let's do one more so you can kind of see. I mean, right now our choices are somewhat limited in terms of the types of functions that we can take the derivative of. How about Well, I'll give you a perfect example of where it helps to understand this idea. What's this derivative? Three x squared radical x plus 1 over x. Tell me what the derivative of this is. So what is f prime of x? That's what we're after. Okay, what's that function that gives you the slope of the tangent at any point? But before I find that derivative, before I use the rule that I just taught you, I'm going to rewrite this. I need to recognize that x squared times radical x is the same thing as x to the 5/2. Because this is x squared, that's x to the 1/2. So it's add the exponents when you multiply. 2 plus 1/2 is 2.5 or 5/2. And then this is x to the negative 1. And now let's bust out with the derivative. The rule, 3 times 5/2 is 15/2. X to the 5/2 minus 1. 5/2 minus 1/2 is 4/2 plus negative 1 x to the negative 2. And then if you want to simplify this and clean it up, that's going to be 15/2. 4/2 is the same as x squared. And then minus 1 over x squared. Okay? So real quick, remember, what is this function that we just found, this derivative? It's a function that tells you the slope of the tangent to this function at any value of x you want. Okay? And once you know that, you can find the equation of a tangent line. So I'm going to run through that one more time. Let's just make up something. Let's say in this particular problem, I want the equation of the tangent line at x equals 1. So in order to do that, I need the slope and I need a point. The point is going to be 1 comma f of 1. So I go back up here to what's f of 1. F of 1 is 3 times 1 times 1 is 3 plus 1, that's 4. So f of 1 is 4. That's my point. My slope is f prime of 1. So now I'm going to go here. What's f prime of 1? That's 15/2 times 1 minus 1. So 15/2 minus 1. So that's 15/2 minus 1, which is 2/2. So that's 13/2. And now my equation of my tangent line, I'll stick it up here so it pops. It's going to be y equals 4 plus slope 13/2 times x minus 1. Okay? So this right here is tangent to that function right there at the point 1, 4. Okay? So that's an example of how to use those 4 rules to find the derivatives using the shortcut rules. I'm going to give you some problems in the Google Classrooms for you to try in your book. I got to decide which ones I want you to do because there are several other rules that we're going to learn, and this is the first of probably several videos on how to do derivative shortcuts. So have fun.